Okay, the formula behind its impedance meter readings is always power is equal to V squared over Z, where power, okay, power is equals in watts, all right, which is what the speaker line will draw from the amplifier, and V is your voltage, okay, and this voltage, because we are using the 100-volt line, is constant, it doesn't change, it's always 100 volts, okay? So if we do V squared, we simply are saying 100 multiplied by 100 volts, okay? That gives us 10,000, okay? Okay, volts, okay? So this stays constant, it doesn't change. It only changes when we deal with a 70-volt system or a 50-volt system. So for us, we use the 100-volt line, so it's always 10,000, okay? Z, in our case, with the impedance meter, Z represents what we call the impedance, okay? The impedance is similar to what we call the resistance, okay? But in our case, we are using a coil, which is a speaker, a coil. In a magnetic field, it creates what we call impedance. So we talk of impedance, not resistance, when we are referring to speakers. All right. So the impedance here is what we measure with the impedance meter. We are measuring the resistance of the line. Then the voltage always stays constant. So how it works with an impedance meter is, whenever we are measuring the impedance, the value, the impedance, it comes in ohms. All right. Comes in ohms. Right. Suppose, for example, I want to know the power the speaker line will draw from my amplifier. We always say 10,000, okay, divided by Z. I take my multimeter, for example, which I'm going to give you a demo. Let's see how much power this line is going to draw. So we go to Z. We now use our impedance meter. Okay. It's a manual impedance meter. There's no polarity. Okay. There's no polarity. You can put the red terminal there, the black terminal there, or vice versa. It doesn't affect anything. There's no polarity. Okay. So for the purposes of the demo, okay, I'm just waiting for another prop. For the purpose of the demo, let's see your settings at the back. Currently, I've got a 7.5 watt, which is a 670 ohm. A 1 kilo ohm will give me 10 watts. A 2 kilo ohm will give me 5 watts. This is on a 100-volt line, black color line. So every speaker doesn't have to be TOA, but every 100-volt line speaker will give you these equivalents. Basically, what they're telling you is, if you measure anything close to 670 ohms, you should technically be powering this speaker with 15 watts. Or if this speaker is tapped at 1 kilo ohms, it's going to demand 10 watts from your amplifier. Okay? So similarly, if this speaker is tapped at 2 kilo ohm, it's going to demand 5 watts from the amplifier. So let's do a test.
So the more the ohms, the lesser the watts.
Yes. The more the ohms, the less the power drawn from the amplifier. Okay. Right now, I don't know what the tapping is on. I'm going to use my impedance meter to measure what it's going to give me. First things first, when you are doing fault finding on a speaker line, the first thing that you do, you plug your impedance meter, you should hear a 1 kilohertz tone playing on all the speakers connected on that line before you even calculate the impedance. This gives you an audio to say, okay, that speaker is working. Any speaker connected to this line, continuous, that does not give you that sound, means that speaker is an open circuit. There's an open circuit connection with that speaker. It's not working. So first things first, connect to a zone, walk through the zone, hear the audio or the sound, the 1 kilohertz coming from each and every speaker on that particular second. Then you are sorted. Thanks, Jacob. Okay, let's do this with the right prop. Same thing. All right. Having determined this, right, the second step is to calculate how much it's reading. Okay, if you look on the meter, it's sitting roughly close to about 2 kilo. Okay. If it was a digital multimeter, it will give you a precise reading. 1.9999 kilo ohm. You round it off to the next digit, 2 kilo ohms. Okay. So what this basically means, this speaker is tapped at 2 kilo ohms, 2000 ohms. Okay. Let's go back to the board to show how much power this is going to demand from my amplifier. What it then means, we come back to our equation. We said for power, we know the impedance. It's now going to be 10,000 divided by 2000, which is 2 kilo ohm. Okay? So all I do the mathematics, 1 there, 5 there. That means that speaker line is going to draw 5 watts from my amplifier. How we use the impedance meter is to determine how much each load, when I connect to my amplifier, is going to demand. Let us assume I have an amplifier here with 2 lines. Okay, there's my hot, my cold. A speaker connected, demanding 5 watts of power. This amplifier, technically speaking, must be able to give me 5 watts or more than 5 watts. If I have an amplifier that gives me 2 watts here, it definitely means I'm going to overpower my amplifier. Similarly, if I was to have a ZM-104A, for example, with 2 speaker lines, okay, which I'll then just correct quickly for the purposes of our demo. Let us assume this is a ZM-104A measured in 360 watts. And we have measured the speaker line. Out of the first speaker line, we have measured line number 1. Okay, it's demanding 300 watts of power. What it then means on a ZM-2000 or a ZM-3000, the left speaker lines from number 2 to number 5, to number 6, will have to share the 60 watts that's left. Okay, if anything, if I add my totals that I've measured with the impedance meter, they go above what the amplifier is capable of producing, I'm definitely overloading the amplifier. Most amplifiers will, on instant, switch on, they will play, then you will see it goes to red, it goes into protection mode. You force it, sometimes when you play soft music, soft volume, you force it, sometimes you find the amplifier will play for a few minutes, then it cuts off. Or you let it play at soft sound continuously, then after a little while, when the amplifier is warmed up, it can cut out. Because remember, impedance is reactive. The more the speaker works, there's nothing in electronics that does not produce heat. The more the speaker works, the characteristics of that speaker changes. So it is important whenever you are working with an impedance meter, whatever you have measured, your Z value, when connected to an amplifier, must always give or leave headroom on the amplifier. I would advise a 360 watt amplifier, for example, to power a 360 watt zone. Yes, it can be done because it's within the same space, 1:1, but I would ideally have a 360 watt power a maximum of 440 watts. This then gives the amplifier a breathing room. When you crank up the volume to maximum, you're not overdriving the amplifier. So the impedance meter is purely designed to do the mathematical calculation that we were going back to, all right? So in our instance, for example, I said the box speaker, I don't know the measurement, by simply putting an impedance meter on my box speaker, I was able to read 2 kilo ohm. That was my Z, okay? So whatever I've found on the impedance meter, divide that number. As long as you are working with a 100-volt line, divide that number into 10,000. That's your simplest mathematics, okay? So in our case, we divided 10,000 divided by 2K. 2K is equivalent to 2,000. That's all I did. So I just went there, cancelled all the zeros, 2 there, 2 there, gave us 5. So I could tell this speaker is going to demand 5 watts. Let us see what is written on that speaker. So far so good? Yeah. Okay, any questions before I go to the speaker? Okay, cool. Sorry? Impedance meter gave us a reading of 2 kilo ohm. Okay, let's do it so that we are sure. I'm going to plug my impedance meter. Gives me a reading of 2 kilo ohm on the back of the speaker. On 100 volt, the black line tells me if this speaker is at 2 kilo ohm, it should draw 5 watt. So our mathematics is all right.
Yeah. Sure. Yeah.
Okay.
Yes.
All right. So this is the bottom line. This is how the impedance meter works. The higher the impedance that you are measuring, the lower the wattage it's going to demand. The lower the wattage you are measuring, the higher the power it's going to demand. So basically, okay, put it back. So once again, I will just remove this. Okay, once again, to demonstrate a short piece of wire, we normally have an open circuit. So an open circuit is what I've done now. I plug in here, there's no ring because the positive is not connected. So this is an open circuit. A short circuit is basically taking this and that together and shorting them out. Check what happens to the impedance meter.
Hey, it's zero down.
It has gone down to 0.
0, yes.
You can see that?
Yes.
Okay? So that means a short circuit, you're going back to 0. It means I've connected a piece of wire across the speaker. It's offering 0 resistance. Okay? So this tells me by merely measuring that that's a dead short. So a short, any reading that you find going towards 0, you must be suspicious of it. It's telling you your amplifier is going to demand more. You're with me? Okay. Let's do again a mathematical proof of what we have found, just on the lower scale. Let us assume that we have measured a speaker line and it has given me 10 ohm reading. Okay. Let's go to the board again just to prove that last point. I'm assuming I've measured my speaker line, and this speaker line is measuring 10 ohms, all right? To determine whether or not I can connect it to a 360 watt amplifier. There's my amplifier, okay? It's supposed to be at 360 watts. However, I've went and measured, my Z is saying I am only 10 ohm, right? Let's do the mathematics. To prove how much power this line is gonna demand, we go again, power is equals to 10,000, all right, divided by 10 ohms that we have read. Okay, if we do that, this speaker line is going to demand 1,000 watts. So technically, there's no way I can connect that speaker line to a 360 watt line.
Yes.
It's not possible.
Yes.
It's way over by almost 3 times of its power.
Yes.
So when you read with an impedance meter, your scale always deflects in this direction. This is 0. This is what we call infinity. Okay, that's open circuit. So this depicts an open circuit. If you put it in on a speaker line, does not deflect at all. It normally depicts an open circuit. If it moves towards 0, especially if it goes straight to 0, that tells you the line is a short circuit. So any reading that goes towards 0, you need to double check why is it going towards 0. It's not always that it is going towards 0 because there's a dead short. It can mean that speaker line has got a long speaker cable run, plus we've got a lot of speakers over there. This is where we come to the speakers now. To move the meter dial away back upwards, what do? We tape our speakers on a different level. So if these speakers were tapped, for example, we have read and it has gone towards 0, and all our speakers, let's assume we have got 100 speakers, okay? They were all tapped at 6 watt tapping. And I realized that if I measure them, they are going towards 0, maybe to 10. What do? I untap them. I can tap them to 3 watt. If they were reading 100 ohm, if I tap them all at 3 watt, you will find that they will read 50 ohm. Okay. If I go to a higher tapping where they will demand 1 watt of power, you might be surprised that the tapping here also will change. So the idea behind this impedance meter is 2. If it stays on the open side, the infinite side, not moving, suspicious, your line is open circuit. If it moves towards 0, be careful, you might be dealing with a short circuit. Ideally, there are 3 scales on the impedance meter. Okay? There's your scale counter from infinity to 0. Then you have got a times 1, a times 10, a times 100. Okay. Sometimes it might move to 0 because you're on a wrong scale. You've got a lot of speaker lines, but you are on a times 1 scale. So you might need to change it to a times 10. It will give you a true reading.
That's what I was going to ask afterwards.
Great stuff. Or you can move to a times 100. So the scaling means you know your installer has installed 10 speaker lines and is on a times 1 scale. So 10 speakers times 6 watt tappings will give you roughly about 60 watts. So you need to know now, okay, how many speakers are on this line and how long is the speaker cable? Because the impedance meter, when it gives you this calculation or this reading that we find here, that reading includes your speaker run cable resistance plus the connected speakers. So we need to be careful what scale to use. So you ask your installer, how many speakers have you got? 15 speakers. How long is your cable run? Plus or minus 20 meters. Then you can expect to use the times 1 scale. Suppose I've got 100 speakers connected and I'm run maybe 300 meters of cable. Obviously, I have to check which is the appropriate scale, either the times 10 or the times 100.
How do you know which one is what?
The best way to prove it is this. I'll show you on the multimeter. The best way to prove it on the impedance meter, if I have, right now, I'm on a times 1 scale, okay, times 1 scale, okay, I'm gonna measure. Let me, so that you can see the difference. Okay, on the times 1 scale, I've got a speaker tapped at 2 kilo ohm. That's a times 1 scale, okay? I'm gonna move my tapping to a times 10. So which means whatever digit that I count here, I multiply by that number by 10. Correct? Okay, so here's my movement. I'm gonna move it, right? Then I'm gonna adjust it to 0 first. So what we do the 0 adjustment because we are on a different scale. Okay. How much are you reading? So you measure, you count from here going
to
this way.
that side.
So that's sitting at about 90.
Around 90 something.
Yeah. So you multiply 90, multiply by, we are on times 10.
There's 9,000.
9,000. Then you divide that number into 10,000. So I've just gone on a different scale.
Then it will still give me 5 watts.
It should, yes, definitely still give you 5 watts. So let's do another one to see if which is the more. We're trying to look for the more precise scale. Let's go to times 100. Okay, right. I'll also zero it.
Wait. So you start reading from here, you go like this.
Yes. So the reading starts from here, going like this.
And when you're starting to do the reading, it has to be at 0.
Yes.
You always reset it to 0.
Yes, you always reset it. Unfortunately, this is an analog meter.
What about the multiplier you were talking about?
The multiplication now, whatever I read here, I should multiply that number by.
Depends by the coupling
100.
here.
Here, there is here.
Yes.
I get your points.
So you're okay. Right now, whatever I'm reading here, I must multiply that number by whatever scale it is. So this is 1:100. So whatever I'm measuring there, multiply by the number by 100. If I move to the next scale, by 10. If I move to the next scale, by 1. You will notice something very funny. That I've moved here, I'm not getting a very precise reading. Okay? So it means, it tells you I'm on a wrong scale.
That even
You can even hear the tone is going down. So I'm on a wrong scale. So what I'll do, I'll move back to my scale times 1 and just readjust it again to make sure I'm sitting on dead 0. Okay, there's a 0 there. That's a 2K. So that's how you determine your scale. So the times 1 scale works for few speakers, okay, not a lot of speakers. The times 10 scale works with, I won't say now average, but let's stick with sort of average number of speakers. It's difficult to define the word average. Maybe 20, 30 speakers. But then the times 100 is a long speaker line with a lot of speakers connected to that speaker line. That's when you use the times 100 scale. So it just basically depends on what scale do you want, how many speakers have you got, and how long is the cable run. So basically here I've proved that 2 kilowatt of power, according to the speaker, according to the impedance meter, on a scale of times 1. If I were to connect 10 of these speakers, if I use this scale, it might work. But if I'm going to connect 20 of these speakers, you might find the times 1 scale might not be enough. I'll then move to the times 10 scale to give me a more precise measurement.
Let me